Hello everyone, thanks for coming. I'm KRZYSZTOF Kotowicz, this is Mike Samuel. We work at Google in the hardening team, the mission of which is to make writing code hard. Well, actually making writing vulnerable code hard, or making it the default case or the easy case to write the secure one. So that's a pretty nice mission. And we're doing that for a couple of years now. So we have quite a bit of experience of trying to secure large code bases that with a relatively small amount of security people. Today, we want to talk to you about one of the most prevalent problems that we have for Google software, at least in the terms of web security, which is DOM-based XSS. We were thinking long for how to protect our applications against XSS in general and DOM XSS in specific, as it suddenly becomes the most prevalent variant of it or most difficult to address. And we think we have a solution that seems to be good enough and worthy of implementation and adoption in not just Google software, but in the web platform, in the browsers in general. And this is exactly what we will talk to you about, and it's called trusted types. And with that, I will hand over to Mike to describe you a little bit of the solution. Later on, I will present a demo because, you know, a picture is worth 1,000 words. A demo is usually a recipe for disaster, especially the live demo. So let's try that. Thanks. Focus that. Focus the. Yeah. Here. Yeah. Yeah. Nope. As you can see, yeah, it's always a bad idea to. Ah, this was tried. Okay. Maybe like this. Yes.
Ah, wonderful. So DOM XSS is actually, if you saw Lucas's talk earlier, it's Google's single largest security problem right now. And the reasons are twofold. One, it's easy to introduce. It's very easy for a developer to write an assignment to inner HTML such that the value assigned is controlled by an attacker. And it's really hard to detect. Automated scanners and code reviewers don't do well when that assignment to inner HTML happens deep inside the guts of some client-side framework. And so we'd like a comprehensive solution. These are our goals. I hope to convince you that we can actually achieve these. So we'd like to fix the root cause. The root cause is that we have these browser APIs, and when an attacker-controlled string reaches them, bad things happen. We want to help developers. So you know, we need to guide developers towards safe abstractions and away from ad hoc methods for creating strings of HTML, CSS, and other micro languages that these DOM APIs consume. And we need to simplify reviews. There's simply no way a small security team is going to be able to review all the changes made by a large group of developers. So we need a mechanism that makes. Thank you. We need a mechanism that makes interactions between developers and security specialists efficient and effective. And there's a huge install base of applications out there, so we need something that works for existing applications. So I'd like to, we've been doing this for server-side XSS for a while, and I'm going to kind of walk you through the claim that we want to build confidence in. So we're secure against DOM XSS because reasons. So what trusted types gives you is if the code is running on a browser that supports trusted types, or you've loaded the trusted types polyfill, then you can opt into trusted types by tweaking a CSP header. So you can see here that the content security policy header has this new clause, which is trusted types. If all you do to your application is enable trusted types, you're going to break your application. But it's instructive to see how it breaks. So with trusted types enabled, DOM syncs only accept trusted values. So a DOM sync is any browser API like inner HTML or source that we need to keep attacker-controlled strings away from. And trusted types guards these syncs, which means that you can't assign untrusted values to these syncs when trusted types is enabled. So with trusted types enabled, this assignment to inner HTML fails. The payload string simply doesn't get assigned. Down here, you can see that I'm using something called a trusted types policy to create a trusted HTML value which can be assigned. So this may seem like a trivial change in semantics, but it actually has far-reaching effects that I'll explain. First, though, there's an awful lot of syncs, more than 60, and so we created a number of different trusted types. So trusted HTML is for syncs that takes strings of HTML, like inner HTML. Trusted script is for JavaScript. A trusted script URL is for a URL that, when loaded, might load code into the application. So a sourced script, for example. And trusted URL is for other URLs, link targets, images, video, audio, that kind of thing. If the only thing we did was prevent string assignment, that wouldn't help much. Some JavaScript developer with a deadline is simply going to create a policy and use it to unwisely mark strings as trusted. So the first thing we realized we needed to do was we need to restrict policy creation. So you can see here my header, trusted types is followed by this name, HTML sanitizer. This is actually a policy name, and so following trusted types is a policy whitelist. If you control this portion of the CSP header, you control which policies can be created. And since all trusted values are created by policies, you effectively control which trusted values can be created. So down here in the JavaScript, you can see we're defining a policy. So this policy can be used to create trusted HTML, but the HTML that it produces is always going to be the result of an HTML sanitizer. So the HTML sanitizer will have removed any powerful elements or attributes before they become the content of this trusted HTML value. And so maybe there's some code deep in a dependency of a dependency of a dependency that thinks it's a good idea to convert Markdown to HTML without sanitizing anything. So since this name, sketchy Markdown to HTML, does not appear in our policy whitelist, this policy will never be created and so will not be a source of trusted HTML values. What this means is, policy code is actually the weakest link in this whole scheme. Policy code needs to be reviewed thoroughly. If you unwisely mark values as trusted, then they can make it through to syncs and mayhem can ensue. So, but this is a much better situation than having to review all the policy code, all of the application code produced by a large application development group. So once you've convinced yourself that the code that affects the results of a policy is legit, your job is done. This allows you, by controlling the whitelist, you can bound the amount of code that you as a security practitioner need to review to be safe against DOM XSS. And what we found, we've been doing this for about 6 years now for server-side XSS, and what we found is that a small number of tools account for the vast majority of policy code. So for example, a strict template system automatically chooses escapers for untrusted values. So the less than script greater than is escaped when it's interpolated. A strict template system is a good producer of trusted HTML values. And it could, in fact, also be a consumer. So if an interpolation was a trusted HTML value, then it can avoid re-escaping that. Sanitizers are another example of a tool. A sanitizer takes in an untrusted string in a language and produces a string in that language without high privilege instructions. So it's another example of a good producer of trusted values. And builder APIs can also be good ways to create trusted values. And these tools like these count for the vast majority of policy code. What this means in the end is that for most projects, you don't actually end up reviewing custom policy code. And since developers have to create trusted HTML values to use within their HTML, or trusted URLs to use as link targets and the like, this guides them, the trusted types kind of guides them towards secure abstractions and away from ad hoc methods. So finally, there are some classes of strings that are almost universally considered okay. It's a big pain to migrate a large application when the majority of what you're doing is saying, oh, it's okay to allow this to assign this to a link target because it's an HTTP URL. The default policy mechanism allows you to easily migrate applications that have this property, where the vast majority of strings fall into a bucket because of some recognizable property. So here you can see that I've whitelisted a policy named default. Default is a special name. The default policy is applied implicitly whenever a string assignment happens. And here I'm defining a default policy for URLs. So if the URL starts with HTTP or HTTPS or mail to, or it doesn't have a protocol, which, according to that line noise, then it's allowed. Otherwise, it throws, hopefully provides the developer with a message which tells them what went wrong and maybe how to follow the approval process if what they're doing really is a legit case. And with this assignment of an HTTPS URL just works. This assignment of a JavaScript URL fails. So we've been doing this for a while now for server-side XSS. And this is actually our main line of defense against XSS for some large, high-profile applications like Gmail and Google+. Here you can see we've got stats from our bug bounty program. Before we started rolling out trusted types for server-side code, the XSS rates were trending up for both applications. It took us a while to migrate these large applications, but as we did so, they dropped off. And then after migration, they've stayed low. So it's hard to come up with clear evidence of efficacy for a lot of security tooling, but this is highly suggestive. And yeah, we've gone and done this kind of widely throughout Google's internal stacks for half a dozen languages with protocol buffers kind of tying things together. And so to recap, if you control the CSP header, then trusted types gives you as a security practitioner the tools to manage DOM XSS. And with trusted types enabled, without trusted types enabled, trust decisions are implicit in their code. There's nothing about the code or the values that get assigned that indicate that these values that the code author intended to trust these values. With trusted types enabled, trust decisions are explicit and auditable. Since trusted types guard syncs, not only are trust decisions explicit, they're consistently checked before values pass to things like the HTML parser or the JavaScript engine where badness happens. with whitelists, with policy whitelists, you can bound the amount of code that you as a member of the security team need to review. These whitelists are very different from CSP whitelists, CSP source whitelists. These whitelists tend to be smaller. They don't need to change when code is reorganized or bundled. Most of the things on these whitelists are a small number of kind of tools with well understood security properties. And what we found is that using these whitelists allows us to guide developers towards safe abstractions and kind of incentivizes investment in security engineering and secure infrastructure. And finally, the default policy and a few other mechanisms are kind of pragmatic choices that we found help to migrate applications to this scheme. And now KRZYSZTOF is going to show you how that works in practice.
Thank you. Okay, Mike. Sorry, I'm shorter than Mike. So let's see some demo. All right, you can see the screen, yes. So there is an application written in Angular framework that intends to, it's an application in which you can search for videos, play them using various backend services like YouTube, SoundCloud, Mixcloud. It's a reasonably complex application. It was written, again, using Angular framework, run-of-the-mill application, an exemplary one. So what we did is we took it and just migrated it to trusted types in a way that's safe, secure, and this is exactly what I will demonstrate, how to actually use the trusted types API in a real-world application. Of course, I can't show you Gmail right now, but something like that. You can later on even check out the code. It's under my GitHub repository in the web project, and trusted types-Angular branch has all the code. So you can follow later on. First of all, Angular, the framework. Nowadays, JavaScript development, or at least for the modern applications, happens usually throughout the frameworks. There are a couple of popular ones like React, Angular, Vue.js, Polymer sometimes. And a lot of those frameworks already try to address the DOM XSS problem. They want to expose APIs to the developers that are safe by construction, or it's really hard to introduce vulnerabilities through them. Therefore, it is safe to assume that, for example, Angular, the framework, especially its, let's say, the template rendering engine, is trusted to produce a trusted HTML value or trusted URL values. Why? Because Angular on its own has its HTML sanitizer inside. It has been reviewed for security. We know of no bypasses for now for that sanitization engine. So it's really, you have to take an effort in your custom code in order to introduce an XSS vulnerability in an Angular application, not AngularJS, Angular, the new one. So what we did is we forked, we have an experimental fork of the Angular framework, simply changing one component of it, making the sanitizer output the trusted values. And the only thing from the application user point of view, or the application author, is to, in the package JSON, just switch one of the packages from Angular to our fork, right? So instead of using the core Angular or vanilla Angular, we're just using a fork, right? This is all that it needs. And as long as the application only uses the Angular way of producing templates and interpolating user data into them, this should be safe because of the sanitizer that Angular uses. So let's try this in action. Spoiler alert, it will not work. Let me actually zoom the thing. And what you can immediately see is something breaks here. This document requires trusted HTML assignment. There's a couple of errors. But you can already see that this is something happening with jQuery. Apparently, this application not only uses Angular, it also uses jQuery. Thankfully, we can see where this actually breaks, right? So jQuery, when loaded, And jQuery is actually not loaded directly. It's loaded through one of the dependencies of the application, namely backbone.js. It does some DOM probing. It tries to do some feature detection on DOM in order to, whatever, code workarounds. So how do we address this without changing jQuery itself? Which is possible, and I also did it, but this is not the part of this demo. Well, we can use the default policy that Mike told you about. The reason why this assignment failed is because we enforced the trusted types, allowing only 3 policies for this particular application. The one that Angular uses, the one that I will talk about later, and the default policy which I will enable right now. So let's enable this, and the application will recompile in the meantime. And let's look at the default policy. So first of all, this application checks if the trusted types API is even available. If it is, then it tries to create the policy named default, which is supposedly whitelisted in the header. And for this policy, if this policy is being called whenever strings are actually assigned to the DOM in the sensitive things. In this particular case, this function is called when HTML things are being called. And what I do here is I have some whitelist of HTML that I simply allow to be written without rewriting the code. And this is exactly what jQuery does when loaded. It tries to insert those strings into the DOM. Clearly, this is not a DOM XSS. There's no JavaScript payload in here, or nothing user controlled. There's also something slightly more custom. They try to inject something that has a dynamic here ID. But with this regular expression being strict, I can make sure that actually there is no bypass that would enable for DOM XSS through this particular vector. So this default policy is being called when the strings are being assigned to the DOM XSS things, and that allows jQuery to work. On top of that, we have a couple of other things. First of all, there's a fallback case if you're trying to, well, essentially load new scripts to the page. And what I have here is also an allowed script regular expressions. There's some widget from YouTube, namely, all right, thank you. There's a widget from YouTube that is being loaded from a URL that's somewhat predictable, but still dynamic. And apart from that, what I do is I just console error just to surface to the developer, you're doing something wrong. Like you're loading an additional script. I know about this, but I will allow for it for now, right? So I just return the input. Whenever you're using other URL things, what I do is I parse the URL, and if you're just using HTTP or HTTPS, I really don't care. You can link to any arbitrary websites, like there's no DOM XSS involved here. And finally, if you want to use eval or other friendly functions, I just disallow it, at least when called with strings. And let's see how this thing works. The application actually reloaded, thanks to the modern development practices of it. But what we can see, what is happening is, yeah, the whole application is working with trusted types under those policies. So we can, look for OWASP, try to, click on the, that's some, yeah, it plays music on my laptop. So you can see the application fully works, like nothing breaks. It was quite easy to migrate to trusted types. What we have right now is we bounded this application to only the code that has access to those policies, those from the index.html. So only this one. So if you're using Angular, whatever Angular does, we trust it. And whatever default policy does, we trust it. In this particular case, this whitelist of HTML, those other things. But let's see about this console error. What's going on? So, there's quite a lot of errors. Let me maybe clear it and refresh. What you can notice is, please refactor script URL. What's going on? Well, thankfully, this is all now part of the code. Like the protection is part of your actual code base, so we can just use regular debugging techniques like just checking in the developer console. All right, so yeah, indeed, there is something loading a Google Analytics script in some file in the application, and this one is using a string for loading that script, which is potentially user-controlled. It's worth looking into. So let's look at this Google Analytics something model.ts in the source code. It's being here, and we have it. However, Thankfully, by making the DOM API strongly typed, we can introduce language level checks or static analysis checks to surface the vulnerabilities. And this is exactly what we did. We have a linter check that warns you that something potentially risky is going on. In this particular case, this resource URL assignment from string might result in script execution and will trigger trusted types violation at runtime. Use the literal policy, right? I mean, you obviously you know that the risk, the potential risk is you do something like this, right? Calculation href here or at the prefix, whatever. Like if there's something attacker controlled, then is wrong. But we can offer fixes for it because, you know, static analysis, it sort of works now if we have types. So this is exactly what I did. And we are using this extra function that magically provides value and security. How does it work? Well, it works like that. As long as this function accepts a string literal, that the assumption is the attacker cannot inject into the string literal. The attacker would need to have a server-side access in order to modify the actual JavaScript code. However, as soon as you want to, say, interpolate data into this, this is potentially attacker controlled, right? So if I use whatever location, sorry, it's curly braces. If I use location, say, whatever, href or hash, right? Or slice, one, the typical DOM accesses. So as soon as you start interpolating into the string, you see that there is actually a problem that even prevents compilation of this code, which we will probably check after a couple of seconds here. Why is that? Yeah, see, so the application, if you try to write a, let's say, a dynamic string or a variable into a sensitive string, this becomes a compilation error. So you get a pretty early feedback for the developer, something is wrong. You should be using a different method. Why is that? It's because this particular function, it uses its own policy called literal script URL, which supposedly does no validation. However, this policy is isolated in this particular module, right? In JavaScript modules, only the exported functions or objects are being able to be called externally. So this policy can only be used from within this module. And the only call side of it is this function, and this function has type annotations, some magic TypeScript, type annotation thing, that makes sure that this behavior is preserved, meaning that only a string literal with no interpolation inside can be the function argument. So even if we did any expression here, this is also an error. So we can be reasonably sure that this is secure. And given that this is a strongly typed, we are leveraging the typed system here, or a more strongly typed language like TypeScript-ish. We can do even automatic refactorings for a lot of the call sites, which lets us migrate the application pretty easily. So in the end, what happens if we actually try to recompile the application using this thing? Did it succeed? Yes, it's compiled. Now this value, the Google Analytics script URL, is not actually, you're a good programmer and you're loading script from Google Analytics. This is part of this literal script policy here somewhere. Yeah. So this value is not going through the default policy, and therefore by migrating your code or getting the warnings or errors through the default policy, you have a chance of migrating the code, the risky code parts into more strict policies, the named policies, and then the default policy can be just like this last resort, log only, report only, or just throw if you're reasonably sure all of the code has been migrated. So trusted type give you a way of locking down the application in a way that is reviewable, auditable, and dramatically reduces the security surface. Because I know for sure right now, in this particular application, I don't have to review a single line of code that doesn't have access to the policy object. Because it cannot possibly introduce the DOM accesses. Because it would only write a string to the DOM, and the strings are disallowed. The default policy would run there. And I guess with that, I can go back to the presentation if everything works. And it doesn't, of course. an easier way, I would just restart the presentation. Oh, come on. Don't look at my password. It's a different one. Amazing. Anyhow, the summary is the same, so we can just go here. So what's the status of the project? We have an implementation in Chrome for a couple of releases now. It changes, and we keep adding stuff to the API. You can use it using the origin trial. It's also created as a spec. This will go through the W3C workflows. We have a discussion group where you can talk to us about using the API. There's a polyfill for other browsers. The code is on GitHub. We are adopting this approach to Google applications. It works promisingly well for now. And internally in Google, we have a whole team working on adopting, creating the API. And we're working on external integrations. DOM Purify is already integrated, so DOM Purify, if the Trusted Types API is available, will produce trusted HTML values, so you get the support for free. We have integrations with other libraries or frameworks planned. We integrate with TypeScript. There's a type definition package already. We do some trials with Angular, with React and other frameworks. And we are set to release some secure policies libraries that offer not just a primitive of the security header and you can create your own policies. We will actually create policies that are safe and are reviewed and we vouch for. Yeah, with that, I guess we can go to Q&A and let's end DOM XSS together. Thank you.
Hello. Sorry if I passed this part. Could you please compare it with CSP version 2 and using unsafe eval? I mean, deprecated on using unsafe eval in it for some web application. Maybe it will be a little bit simpler way to prevent DOM-based XSS.
CSP doesn't prevent XSS, it rather tries to mitigate the exploits that come from the XSS. We act more early. We try to prevent the injections in the first place instead of trying to make sure that the injections don't contain JavaScript is what CSP tries to address. But in specific, what we find CSP, after years of experience, what we find CSP good at is at preventing or mitigating the server-side XSS, the stored and reflected in specific, especially the nonce-based variant of CSP. However, for DOM XSS, it's just not best. I mean, we see a lot of DOM XSS ends up being a property of the JavaScript program. And you can't easily tune that by just looking at the URLs of the scripts or maybe looking at eval only, right? So lack of unsafe eval in CSP can only make sure that you're not using eval. With trusted types, you get to instruct eval what to execute. So for example, it's way easier to migrate an application that uses eval selectively in some call sites to trusted types than it would be to remove the eval capability completely that is required by CSP, sort of. So by using trusted types, you get more control into how your interactions with the DOM look like, including the eval function. With CSP, it's more like it's binary thing, like, okay, so you can load scripts from this URL, or it needs to have a nonce, or you can use eval or you cannot use eval. It's a decision of the policy author.
But at the same time, unsafe eval is not only about eval constructions, but it's about the whole constructions like inner HTML and so on. So you can try simply not to include unsafe eval in your content security policy, and it will help you to mitigate DOM-based access. Isn't it true?
Yes, CSP helps mitigate DOM XSS. That is a true statement. It doesn't prevent the injections though. So for example, with, let's say, a hardened version of the CSP, you didn't remove the injection point. The attacker can still inject arbitrary HTML and just, create a spoofing, create a credential exfiltrating page. They can do it. There's no script there. It's just, graphics and a form field. And with trusted types, we try to prevent the injections, not the JavaScript execution from those injections.
Okay, thank you.
Thank you very much. Thank you, Christoph and Mike.